everybody. My name is Anna Förster. I'm from the University of Bremen in Germany, and I'm very happy to welcome you to the very first edition of our brand new seminar called Connect Them All. So connect everything which is around you to each other and to yourself. And I'm very happy to be co-organizing that with my colleagues. Frederick is today here with us.
Yes.
Pietro Manzoni from Spain and Marco Zenaro from Italy will be joining us in next editions. So I will now hand directly to Frederick, who will be presenting our very first special speaker today. And I hope to see you again in the next sessions too. Thank you.
So thank you very much, Anna. I'll take it from here. So let's invite Florian to the stream. So welcome, Florian. And just a quick word. So I'm in Kalmar, and Anna is who recently said welcome to everyone. She's in Bremen, and Florian, you're in Aarhus.
I'm living in Aarhus in Denmark. Yes.
Yeah. So we sort of have connected the dots on the map now. So we could say that you're sort of in between Kalmar and Bremen. Not really, but almost.
Close enough.
Yeah, close enough. So you've been invited here today as the first guest of the Connect Them All seminar series. And you've been like especially pinpointed by me, actually, because I think that you are making so interesting development in the area of IoT. So it's really worth lifting up, as I see it. So, and well, you might want to introduce yourself, but I could at least read a little bit from your bio. You did your PhD in compiler technologies. That's correct?
That is correct, yes.
Yeah. And like you compiling scheme to JavaScript, you worked on Google, and you worked with the JavaScript engine in the Google Chrome browser.
Bit, yes, yeah.
Yeah. And you've also worked with Dart programming language.
That was a big, nice project, yes.
Yeah.
That was a great project.
Yeah, I know very little about the Dart programming language. So, yeah. And then you have, since the last 5 years, is that correct, worked with Toit?
I think it's 4 years now. I think it's 4 years, yeah.
Yeah.
But yeah, 4 to 5 years. It's getting longer and longer, yes.
Yeah. And you're one of how many co-founders of Toit?
We are now we are 3 co-founders left. There are a few co-founders that had one went to retirement and one went away, but we are 3 co-founders left, all of them from Google, and it's a great project.
Yeah, and you're like in that like bubbling ecosystem of IT companies in Aarhus, because I understand that it's a lot of things that are happening in Aarhus in this area, or
yeah, for some reason Aarhus is a technology hotspot. It's probably because it has a big university and lots of students. But we have Google here, Uber, all the big ones are basically in Aarhus, and yeah, that's where IT is happening in Denmark.
Yeah. So perhaps you want to mention anything more about yourself, and you're happy to do so. But otherwise, I'll actually start up you have a screen presentation, and you also have a presentation that you want to share with us. So
yes,
yeah, and we can
Thank
see
you.
that now. So it looks perfect.
Just put it online.
Yeah,
I mean, put it on full screen. Thank you. Yes, as Fredrik said, I'm going to talk about our project Toit, which I just basically say it's a modern framework for IoT. And before I explain more about Toit and a little bit also about us in general, I wanted to give a small introduction of where this whole thing comes from. Why did we even do this? And the biggest thing that started this was probably the ESP32. It's a small microcontroller with 520 kilobytes of RAM, 4 megahertz of flash, runs at 240 megahertz, has tons of peripherals, Wi-Fi, Bluetooth, converters, all kinds of things, and it's super cheap. You can actually go to AliExpress or Alibaba and get them for less than $2, and that's the price you pay as an individual. So it's really cheap. This is an action image of one of those modules, and it's just great. It's a nice toy to play with. It's so really powerful, but the thing that we noticed a few years ago is that it's still basically treated like the old microcontrollers from 20 years ago. I did play a little bit at university with robotics, and we had these Atmel 8-bit microcontrollers, and working on the ESP32 still felt like working on these 8-bit microcontrollers from 20 years ago. You flashed the whole thing at once. There was no notion of applications, no memory safety. If you crash on one end, the whole thing goes down. And they're also not really high-level languages. So there's MicroPython, CircuitPython is the most famous one in trying to get onto these small microcontrollers. It's just not a great experience with MicroPython. And then the other languages that are currently trying to get there a little bit to Rust and Go are not really the high-level languages that I think of when I think of high-level. So basically, our goal was to change this. We wanted to make, and given that these chips are actually quite powerful, we wanted to make them much, much more like real computers in some sense. And here's now a small introduction of who we is in that context. So Eric, Casper, and me, we met at Google more than 10 years ago now, and have been working, and I think I have this on the next slide. Yes. We have been working on V8, JavaScript, and Flutter, and some of the co-founders also worked on Java. That was not me, though. Fredrik said that he doesn't know a lot about Dart, but Dart is definitely getting more and more popular because Flutter is used more and more, and Flutter is a great framework to write applications for iOS and Android. So the Dart programming language is actually becoming more and more popular. So now, when I said we wanted to change this, what exactly did we want to change? And here's a little bit of a high-level view of this. When you currently program the ESP32, you use the ESP-IDF, which is just a framework at the bottom, and then you used to, without Toit, you have this whole firmware that you just put onto it, and that's it. It's one big application. And what we would like to have instead is have a virtual machine on top, where we then can have separate applications that are memory isolated, that you can install, uninstall, that just feel like much, much more like a real computer. And in order to do that, we had to basically, we ended up creating a new programming language.
Yeah, and Florian, I guess that you might be coming to this later on, but I guess that many people they say, well, why yet another programming language?
It's a good question, and I don't actually have good slides for this, so I might as well just do this now. So one of the reasons, and I will just try to find it. I didn't prepare this well enough, but I think I have benchmarks. Let me get through. If you run Python and you compare it with Toit, and I will use. Again, I think I actually have to open. Yes. And I compared with speed of Toit, then even on the desktop where Python is doing pretty well, this is a completely recent version of Python. We are still significantly faster. And on devices, we ended up measuring a factor of 10 or more. And this is with a Toit version where the compiler hasn't actually been optimized very much yet. We picked the really low-hanging fruits, but we have, for instance, not really implemented inlining yet. So there are still significant amount of speed we can win from the current language. And no, that's not what I wanted. And so Toit is, for one, significantly faster. And it also uses memory in a better way. And the reason for that is not just because the implementation is well done. A lot of the developers at Toitware have worked on virtual machines before. It's also that the Python language, for instance, doesn't really allow you to optimize many things. It's too dynamic in some areas that make it hard to optimize in a resource-constrained environment. And the same is true for JavaScript. JavaScript, just as an example, allows you to change the shape of an object. You can add a field at a later point to an object. These kind of things can be quite annoying when you write the virtual machine, but they also make it significantly slower unless you have a lot of caching and memory to make this much better, as is the case in browsers. So we went. I mean, the initial attempt of Toit was actually looking at Python and trying to make this a fast language for the microcontrollers, and then basically gave up. The other reason is that clearly, I mean, we like doing languages. We did Dart before. We have a little bit of experience in that, and we felt like there is no real good new modern programming language that fits well to be optimized for microcontrollers.
Yeah.
And with that, we then ended up doing our own programming language.
Yeah, and also one follow-up question on what you showed previously. Like, well, it's quite obvious now that you're working with the ESP32 from your previous slides, and also by looking at your homepage, it looks like that's the microcontroller, that's the hardware that Toit is supporting at this moment. So, is this a clear explanation for why the ESP32 was the obvious choice here, or?
So I think the ESP32 is currently probably one of the best, if not the best, microcontroller, especially if you take the price into account. The Toit language itself and the Toit framework itself does not require the ESP32. It's just we need to focus on one chip first, make this great, and then you can branch out. But getting every peripheral of a microcontroller to work is actually quite time consuming. So instead of having 10 chips that all of them work just a little bit, we prefer to focus on one and make that one really, really great. That said, we recently did at least branch a little bit. We're starting to support more than just the ESP32. We're starting to support the ESP32 S2, C3, S3, so different versions of the ESP32. It's still expressive. That is true. It's still the same framework underneath, but fundamentally we could switch to a different chip as long as it's strong enough.
Yeah, I got a question from the chat and from Kwong, and the question is like, doesn't the virtual machine demand an operating system? So a virtual machine does not necessarily need an operating system, but we do use FreeRTOS underneath. It's mainly for avoiding to write too much on our own, but in theory, the virtual machine could talk directly to everything, to the chip. It's just that the work has been done already, and it's a significant amount of work that would need to be redone. So we basically put the virtual machine just on top of the FreeRTOS system. Okay, yeah, I think that was a clear answer.
Good. So yeah, so this is the Toit programming language. We created that one, and the next 3 slides are just showing how that looks like. It's indentation based, so it's inspired by Python in that way, and the calls are without parentheses, and that's inspired by probably Bash and Camel, and it's very lean, I would say. The idea at least was that it should be lean. So here's a hello world with a local variable. Here is just functions, and the reason for this, I mean, I can show how functions look, but also it shows how we have optional types. So you can add types if you want to, and the /int is one, and the arrow int is the return type here. So Toit, yeah, this is just showing how to do simple stuff in Toit. We obviously have a lot of libraries to interact with the device. So I2C is a common protocol to talk to devices, to sensors and so on, and I will use this in the demo just afterwards. And the GPIO pins are accessing the individual pins of the ESP32. You can also see on this example that we have named arguments that start with --. So this is probably inspired most by Bash again, but it turned out to be one of the best choices we made in Toit. It feels really nice. So how hard is it to use Toit? This was another thing we always hated with embedded development, and in Toit, it's actually really easy. There's no makefiles or tool change or anything. You basically get Toit from our open source repository. That's one option, and the next slide I will show another. And then we have lots of packages on package.io. So basically the whole thing is open source, but in order to make things easier, we have, especially for the ESP32, we have Jaguar, which bundles this whole thing up for you. And you can just get Jaguar on most platforms with one line. So you say brew install on Mac, Winget on Windows, and if you have Arch Linux, you can use Yay. If you don't have Arch Linux, you can just download the executables from our GitHub builder, so you can even be more or less sure that it has been done without any changes to what happened on the open source on the GitHub.
And Jaguar is the application that also flashes the firmware, or is that correct? Or
yeah, so basically what we did, we split Toit into two. One is the language, libraries, and so on. And then we have Jaguar, which is a small tool that makes it easier to work with the ESP32. So it has support for flashing. It has support for installing the applications and similar things. So that Jaguar is basically making the goal that I showed before this picture happen. The Toit is just the framework, the language underneath that is used by Jaguar to do it. And I think it will probably become a little bit easier with the demo that I'm going to do now.
Yeah.
Let's see if I can find this. So the best way to work with Toit at the moment is probably with Visual Studio Code. And the easiest is you just take a directory and start Visual Studio Code in it, as I'm doing now. And then let's go into full screen mode here. Go away. And let's get a terminal. So Jaguar is it's installed here. I mean, you could just install it, as I said, with one line, but it's probably fine. Similarly, Visual Studio Code here is set up to use Jaguar, so you can download the extension, the Toit extension, and it will automatically find Jaguar in your path and then highlight and code completion using Jaguar. So the first thing we probably want to do is install Toit onto an ESP32 device now. So I have on my desk an ESP32 device, and I have a webcam pointing to it. So this is the ESP32.
Yeah.
The camera has a lot of troubles with focus, but it's not that important. And it's connected to my serial port. So I'm now going to just say Jag Flash, and that will now flash Jaguar. I will now flash Toit and Jaguar onto the device. From that moment on, there will be this now basically makes the ESP-IDF on the bottom, the image that we had before, and the Toit virtual machine, which is above, that is now installed onto the ESP32. And in addition, we have a small program already installed that is responsible for being able to update, install, uninstall applications.
So the application on the device now, you call it a Jaguar application that is also now on the ESP32.
Yes, correct. Yeah. And if I now monitor the device, so if I look at the serial output of the device, it tells me actually that it's starting Toit in the beginning, Alpha 37, and Jaguar is also running, and it's running, and the device is called Red Interest. We always give a random name to our devices when we flash, and it's basically ready to listen on its IP address. And the Jaguar executable now is going to talk to the device using that IP address and that port number. So I'm going to add a new port. I actually have already some, but it's not important. So no, that's not what I wanted. Sorry. I'm going to split this one, if I can, into two. So I will keep the monitor on the left because this is where we can see messages from the device, and I will have another tab on the right with where I will run commands. And I think we should just start with the hello world. So I'm going to create a new file, save it immediately as hello Toit, and just do it, print hello world. And if I now run this, and I'm back at the bottom of the right, check run of hello.toit, you can see on the left, so it asks me which device it wants to run on, and we will pick the red interest, the one we just flashed. And you can see on the bottom left that it printed out the hello world.
Yeah, and if I look here, it seems it is communicating over Wi-Fi at this moment.
Correct.
So not the serial port. So
yes, so we use the serial port on the left to see the messages, but the actual communication between the Django executable and the device are done over Wi-Fi. Okay. So you can basically update a device over Wi-Fi. The fact that the messages are printed on the serial port is just because we haven't done the piping it through the Wi-Fi yet. It's possible, but we just haven't finished it yet.
Yeah.
So one of the things that's happening, one thing to note is here that installing that hello world was extremely fast, contrary to reflashing things. And the other one is, and because of that, we actually also have a command to just say watch a file for changes. So I'm calling on the right now, Django watch the hello. It immediately starts it again. So you saw the hello world on the left. But if I now go here and add a few exclamation points and now I press save, it basically automatically compiles it again. I save again. It automatically compiles it and sends it to the other side and runs it there.
Yeah.
So this is a way of it's an extremely fast development process. And with that, I'm going to make a few examples of how to do it. I'm hoping I should hopefully be fast enough to show a few things that are nice.
Yeah, so, and also when you're showing this, I see that your editor is actually seeing that this is the Toit language that you're writing. So there is an extension as well for VS Code.
Yes. So we having an extended Toit extension. You can just install the VS Code extension, and then it finds Django and will automatically code complete, syntax highlight, and all the things that are nice. And there are also a few commands that we provide with the extension, but to be honest, I always use the command line. I don't even remember the names of the commands that come with Visual Studio Code. But yeah. And you can also see that here the completion, for instance, of what is possible. The libraries, imports, and so on. So this works quite nicely. So we're going to, I think we should just, let's just do a small LED example as well, because this is the hello world of the embedded world. So we want to have a pin that is a GPIO.pin, and I note that I have an LED on pin 32. And so this is interesting. Just to this completion is from GitHub Copilot. In this case, it's actually wrong, but the Copilot works quite nicely with Toit if you have a little bit of codes in your environment. So, for instance, here GitHub Copilot will automatically suggest the correct code. So since I'm still watching on the bottom right with Django Watch, I just need to save now. And the program will be again compiled and it started. And now if I switch back to the camera, it's out of focus, but it's clear that the LED is blinking. Yes.
Yeah.
And again, nice thing, I can go back here, change it to 250, save, and it immediately works. So let's go back to writing. Now I wanted to show another sensor on that board. That's the that's grade C, and that's the BME280, which is a temperature sensor. The BME280 is a Bosch sensor, and we have a package for this. So on the bottom right, I'm now installing a package. package install BME 280. And once that's installed, I can just import the install library and use that. So the BME 280 is on an I2C bus. So we will need to get the bus first. For that, we create a bus, and we need to give it the clock, which is on GPIO pin, I've written that down, 26. And we need to give it the data line, which is on GPIO pin 25. And now we can scan the bus and immediately print the result. Let's just do that. I'll save, but I need to watch again. Watch here. And it ran, and it tells me down there that it's found 3 devices with the IDs 96, 105, and 119.
Yeah, and I saw from your video that you have actually 3 devices there. Yeah. Okay.
Yeah, so we have 3 red devices which represent the 3 I2C. I mean, again, out of focus, but it's the 3 3 SparkFun sensors that are all on I2C. And one of them is the BME 280. I could now basically try to figure out which of the numbers is the BME 280, but we can make our life a little bit easier. We can get device by just saying bus.device of the BME 280.I2C address. As you can see, there are 2 of them. We don't know which one is the default. I actually do, but for the purpose of the demo, I will do as if I didn't. And we'll create a BME driver, which is yes. Then we can just print BME.read temperature. And then you can all see how nicely warm it is in my apartment. So you can see there's an error here. It couldn't read the register, and that's because this SparkFun sensor is actually running on the alternative one. So if I save here again with the alternative one, now it's restarted, and it tells me that currently it's 24 degrees in my apartment. Yeah, so this is another small demo I wanted to show, but I will continue with the demo because I'm going to use this in the next later. I'm also going to check package install the HTTP package.
And one question about the package install. So these packages are installed in your project folder, which you're within. So they are not installed globally in the system, or
no. So we made it such that we have a package YAML and a package log file that basically keep track of which packages are installed. And in your project folder, you also have a .packages where we download each individual package.
Yeah.
So this way you have separated packages. You should normally not modify them, but it's nice that because it's separated for each one, you can go in and change them if you want to play around with that. Again, generally you're not supposed to go into the .packages.
Yeah. And I got a question here: is there any emulation for like sensors? Well, if you don't have the sensors, are you able to emulate these things?
Not really. I think at the end of the presentation, it will be clear of where we want to go and why this shouldn't be as necessary. But at the moment, usually you actually get the sensors, yes.
Yeah. And you got also a comment like brilliant demonstration. So keep up the good work.
Thank you.
Live demonstrations are always much more fun to watch. So
that's good to hear. So yes, I will just continue, and I will keep it called Hello Toit, but watch it again. And we'll continue with the HTTP library. So the HTTP library requires also network, and I think I mentioned it a little bit, but it's still worth pointing out again. These small devices that cost less than $2 have Bluetooth and Wi-Fi included, so they're just extremely nice to work with. And in order to create a network, so what I'm going to do now is I'm creating an HTTP server I can connect to. So I will start by opening the network, then create a socket. Listen, I'm going to listen on port 1, 2, 3, 4. And now I'm going to use the HTTP package that I just downloaded, which has a server in it. And then on that server, I'm going to listen using the socket that I created before. And now there's a small Toit thing that I don't have the time to really explain, but the colon basically means I'm giving a function, a lambda, to the listen. And that lambda will get a request and will get a response writer to write the response into. So I can now say I got a request here, and the path of the request is request.path. We're using string interpolation, which is nowadays basically standards. A few years ago, this was not yet. I would have needed to explain what this dollar means. And if I Control S, if I press save, well, it started, but might be nice if we actually get a line that tells us where to listen on. And it's, I think it's like this. And the port is 1, 2, 3, 4. And let's make it even easier by putting the HTTP in front. So if I save again, immediately on the bottom left, it will tell me where it's listening on.
Yeah.
And if I take this, copy, and show a simple browser here, it tells me at the bottom that it got a request to /VS Code browser require whatever. So it's responding. Or at least it's getting the requests, and now we need to respond. So bring up a little bit. Now we say writer write. We're using multi-line strings here, and we're returning a string with HTML. And now I very much like Copilot because it basically just did the whole thing.
Yeah, it's good at doing its job sometimes. Yeah.
Sometimes it just works.
Yeah.
And I think it actually did the right thing here. So I will save again. We'll now again listen here. I'm going back to the simple browser, reload, and now you also have my pressure and humidity. So this was all that was needed to get a small HTTP server with that shows me my temperature. So I'm going back to the presentation now, but there will be more demos in a few minutes or in a few slides. So fundamentally, this is just a recap of what just happened. I showed how to load, to install, run applications. I haven't installed them yet. We'll come to that, and show how this whole thing works. So there's a very fast development cycle. You just write code and refresh and save and auto and all of this. And we hooked up a BME 280 sensor. So this is now the zoom in of what is under my camera there. The sensor is actually just a small thing in the center there. And what I haven't shown you yet is how to actually install applications. And I will first show on the slides how that works and then do it in practice. So we do now have this ESP-IDF at the bottom with the virtual machine. When I called Jaguar run or Jaguar watch, it used an application on the virtual machine to then run that thing that I sent there. But what you really want is to install applications so that when you reset the device, for instance, they start running when the device boots. And in order to do that, we have the check container command, where you can install, this is just an example, you can install an NTP service, you can install the BME 280, another main, you can just install things and you can list them later.
And when we talk about containers, we are not talking about Docker containers, but we are using the same sort of abstraction for running programs. Or
it's basically a normal application, a normal program. It's a little bit more because we can bundle most stuff with it, but it's fundamentally yes, and just an application. Yeah. And it's there's a reason it's called app on the left side and not container.
Yeah. And you're able to exchange variables between the applications, or
so that's one of the nice and hard things at the same time. These applications are separated, isolated, so you cannot just reach into the other application and give and change its memory. However, there is a protocol to talk to each other, and this is what I'm going to show in the next actual demo. So this is pretty much perfect time. So I'm going to go back here and want to show something that, but basically I'm going to show how to talk to each other between two applications now. And what I'm going to do is I'm going to split this program into two, one where you read the temperature and one that serves the HTTP request. And I'm considering the HTTP program the real application, and the one that reads the temperature just basically, it's fundamentally a driver. In the sense of a Linux driver. So I'm creating a new file and I'm calling it service. I mean, it's not a great name, but not. And I'm copying over the whole hello world, the whole hello Toit file here, and removing the HTTP part. So just going back to printing the temperature of the BME. So we're back to where we were 10 minutes ago, probably. And if I go back down there and I run this, I will just run it this time. Right. I run it, it will basically do the same thing as we did before. It prints the, I can remove this now. It creates a device and then prints the temperature. And now this is where things get interesting. Casper, we haven't published this yet, so this is very much work in progress, but it should give an idea of where we want to go. So there's a package that represents common interfaces, common APIs for sensors, and it's aptly called sensors. So I'm going to install this now, check package install. And the problem is that hasn't been published yet, so I need to do a little bit of funky things here. It's a local package because it's on my drive only, and its name is sensors. And it's actually just here. So I have now installed this package, which hasn't been published yet, but eventually it will. And this package, as I said, is basically representing an API for common sensors. So I'm importing this now. Finish it for it. And I want the temperature. And we are now creating a new class, BME 280 service, that extends the temperature service. And when you hover over the error message, it already says the main thing it's missing is a read function. It already does all the service part, but it needs to know how to get the temperature. And for that we need a BME sender and a driver. So this is a way of saying I have a BME field underscore, just to say it's private, of type BME 280 driver, and I'm creating a constructor that sets that field. The .bme underscore just says put it into the field. I don't need to do this. The dot basically just sets the field automatically. It's equivalent to saying this .bme equals the argument and so on. And we need to call the super here, and with a name. I just know that, and a major number, 0, and a minor number. Let's just call it 1. And as I said before, we still need to actually implement the read function. So with that, we have now a service which uses a lot of the temperature service base class that I imported. That makes it possible to talk to other applications. So we still now need to create the BME sender because we need to pass this into the service. We're not going to print anything here, and we're going to create a service that is BME service with the BME sender, and then we're going to install it. And with that install call, we tell the system that it should make this service available to other applications.
Yeah.
And we're going to this time check container install this temp service and make this a little bigger. Temp service. And it's the service.toit. And now we're installing that service. That for one means there's an application installed now, and the other one is if I restart the ESP32, it will find it again. And I can now check container list, to see the installed applications. The temp service is now installed, and the other one is the Jaguar, which, as I said, is installed by default so that you can actually talk to the device.
Yeah.
And now, once we have this service installed, we can go back to the Hello application and drop all the things that are related to the sensor. And now we have obviously a problem that we don't know what to do here. And for one, we are not going to do the pressure and humidity this time. But we don't need the service again. We need a way to talk to that service that we just installed. And for that, we install the service. We import the sensors, the same package as the service uses. But we this time want to have the client for this. Client. And by just saying which one we want, the client function itself will do everything that is necessary to find the correct application that is installed, the correct container, establish the connection, and make everything work. And now inside our HTML, we can just say client.read. And this will now do a remote procedure call to the container that runs the BME 280 thing. So I'm going to check run this now again. And it should install itself. It should listen again. This should be the same address, but just to be sure, let's copy it. Go to the simple browser. Refresh. And it works because it's only showing the temperature. So the really, really nice thing here is now that the demo application knows nothing about the sensor anymore. It doesn't even know which sensor we use. It doesn't know on which port it is, which pins it uses. It just uses a service that gives the temperature. And this is now coming back to the question, can you emulate hardware? You can't, but you can definitely emulate a service. You can just provide a service that returns different temperatures the way you want them.
Yeah.
So that makes it very nice. And to finish this part off, and I don't have much after that.
And in this case, you can sort of, when you're doing some kind of development, I guess that you can write your applications for different types of sensors and like then using this service function and implementing them in other applications. And
perfect timing, because that's exactly what I wanted to show.
Yeah, and so this is not prepared, Florian. Just to the audience know that actually we haven't talked about this before.
So in this is basically I have installed a small TS18B20, I think it's the name, temperature sensor here. So it's a different temperature sensor than the BME 280, and it's a different board. And I have prepared this board, so it has already a temperature container in it. So I will go back to. You can see the port was closed, so I reopen it to listen to the new port now, and you can see that the temperature service has started, and the name this time of the device is normal reaction. So we're going to switch to normal reaction with scan. You can just okay. With scan, it tells you which devices there are. Let's make it nicer. And I will pick the normal reaction that I just connected. And then, no, let's make this. If I container list, it now almost. It does show me that I have Jaguar and temp service installed. So I already did the service for this device with the other sensor. But if I now say jag run of the same hello Toit that I just wrote, so no changes to that code at all. You can see on the left, it started up the HTTP. This time we do have a different IP address because it's a different device. Copy. And if we go into the browser here, and refresh, we can see that this one thinks it's a little bit colder here. And that's it. I would have a third temperature sensor as well, but I don't think that's necessary, and we're running a little bit out of time. But you can now basically create temperature sensor drivers and write your applications same as on Linux, where you don't know which sound card you use. You just know there's a sound interface, you use that, and that's it. So the feeling becomes much, much more like a real computer.
Yeah. So are the virtual machine using both cores of the ESP32 or?
Yes.
Yeah.
We use as many cores. I mean, we use the cores when possible. The individual applications are single-threaded cooperative threads, so you can have multiple things running at the same, cooperatively, but you can have the individual applications can run in parallel, and we do use multiple threads anyway because of doing stuff in the background.
Yeah. So what's the limit of like how many applications can you run at the same time?
The sky is your limit, and with sky it's the memory this time.
Yeah.
So basically, as long as you have memory, you can run as many as you want. Usually, I would say, I think a stack probably requires 4K. So you need at least 4K usually. And the devices, even though they advertise a lot of memory, they also use a lot of memory by default, just for their own caching and for Wi-Fi and similar things. So you cannot run too many at the same time. TLS is also a memory-hungry thing. But if you don't use TLS or Wi-Fi, or depending on what you use, you can run quite a few of those applications. But you usually end up running more tasks instead of applications. But maybe for 8K, I don't remember exactly how much you need.
Yeah.
But you can run quite a few. Quite a few. A handful probably at least. We don't often do many more. To go through the service is basically, as I said, you can abstract away the temperatures service and show and have different implementations. This is summarizing the advantages. It allows you to have different versions of your actual hardware, and if you run out of components, which definitely did happen recently to lots of people, you can update more easily. You just write a new service, you get it up running, and you're safe. The other advantage is that you can actually use it among many applications. If you have one temperature sensor service, you can have 2 or 3 applications that access the same service without needing to reserve the pin and interfering with each other. Yeah, with that, I'm actually getting to the conclusion. So Toit is a high-level open source language, so everything you saw today is open source, and we're working in the open first, so we don't even push, we work there. And it's great for network, for ESP32 devices in general. Anything that is on the ESP32 is pretty nice. What we have implemented, and that is a lot, works really nicely with Toit. We worked on things like Chrome and Flutter before, just to basically give a little bit of pad on our shoulders. It has advantages to things, to the small, to C-like programs. You do have memory isolation. I didn't show, for instance, what happens if there's a crash. You just get a stack trace, nothing that your own application stops, but the others continue working. It has significant advantages. And compared to MicroPython, because that is the usual thing, it is more stable and more robust. MicroPython does have memory issues, and it sometimes doesn't feel production ready. We also have great support for over-the-air update. You kind of see that because every time I said run, it updated an application. But we also have ways of updating the whole firmware and similar things. The underlying virtual machine and ESP IDF. Most people use Jaguar to develop the ESP32. Even that said, we do write our own tools. A lot of them, at least, in Toit. It's a very nice language to write programs for the command line as well. And with that, if there are questions, I will hop on the YouTube channel and answer them there.
Yeah. There are some questions here, like I can read it out loud.
Sure.
This is great concerning the portability, but is there really business cases for multiple services when the units are so cheap and the hardware doesn't really need to be shared?
It's more about that if you have, so you write your, I think there are 2 different things here. One is you want to be able to replace a temperature sensor if it runs out of stock. So if I'm currently running with the DS18B20, I think that's the name, and that one runs out of stock, I can switch to the BME280 and it's going to work. I think it's different. It doesn't matter. The other one is that if you have 3 different applications on your ESP32, you can obviously put them together and then make that work. But it's just conceptually nicer if you have 3 different applications and they talk to one sensor only. You don't want to have 3 sensors just to make the applications nicely separated. Did I get the question correctly, or is that?
Yeah, I think so. Otherwise, we could probably extend that in the chat later on. So, not sure. So
I will be on the chat.
Yeah, one question I have also is regarding deep sleep. That if you want to optimize the battery consumption, I guess
that's we basically the only way you can actually run an ESP32 with on battery is to sleep. It's the ESP32 is quite power hungry, and you cannot really do anything else than say I'm going into deep sleep. And we do support deep sleep. Deep sleep is fundamentally just a call to say go into deep sleep and wake up with a certain reason, either because somebody touched a pin, or because the time expired, or maybe there's some, and a pin went high. But fundamentally, these are the 3 most important reasons. And from that point of view, we expose that function. You just call deep sleep with 5 seconds, and then it will go to sleep for 5 seconds and then boot up fresh. So we don't have a way of keeping, we don't store the active memory anywhere. So you basically just reboot after that, which is the common way of doing it on the ESP32.
Yeah. And one other question, I mean, you build the virtual machine, you said is running on FreeRTOS. Then like, are you able to use Toit as an RTOS, as a RTOS? So
a real-time system.
Yeah.
So fundamentally, we are not real-time. We have a garbage collector, which can take a little bit of time. It's given the memory situation, it's usually not bad, because going through 300K of memory doesn't take a lot of time, even on devices that aren't that fast. But it's clear that if you need a precise timing, you don't want to do it in Toit. That said, it's extremely rare that you actually run into this. I have written a lot of drivers and a lot of applications now with Toit, and I have only one case that I'm wondering how I want to do it correctly, because I have tight concerns. But the reason is that the ESP32, the chip itself, does a lot of work for you. So if you want to, for instance, talk one wire, which is what I'm doing on the temperature sensor that I just showed. One wire has precise timing. It's not supported by the ESP32, but the ESP32 has an infrared remote protocol, which allows you to be microsecond precise. So you say, I want to send this pattern out, and it will just do this. Similarly, our LED strips, in theory, when you write LED strips, you need to have a very precise timing to get each LED strip's pixel with the correct color. Well, we use the hardware for that. The current implementation uses an UART and basically makes the bytes in such a way that it's interpreted by the LED correctly. We could also use the infrared protocol to do this, but you very, very rarely need to actually have precise timing inside Toit. You usually just let the devices underneath do it for you.
Yeah. And you mentioned earlier tasks earlier, that you didn't really show that, or did I miss it in that case?
No, I did not. I did not show tasks. Tasks are fundamentally cooperative threads. So when you write task and give it a lambda function, that will then run on its own until it yields, and then the next one runs until that one yields, and it's basically you do your stuff until you give you let somebody else do something else.
So you could write like multiple applications and do them in this containerized way, or you could write also, well, everything in tasks in one application and sort of achieve the same end goal. Or do I understand it correctly?
The difference between tasks and different applications is that tasks share memory. So that is the main reason you would want it to be, and it's also cheaper. But for instance, if you have an HTTP server, the moment that when you say listen to, well, that's actually an example. But if you listen for UART, for instance, then when you listen, you are going to block on that port to say until you get data. And the way you usually do this is you create a task that will then listen on that UART port, on the serial port, and in the meantime, you do your other things. And then when the UART port finally has data, the moment the task has a chance to run again, which is usually happening quite frequently anyway, unless you run a while loop, a while true loop without any sleeping and so on, that happens pretty much automatically when you, happens just. Then that one continues running. So,
let's skip to the questions on the chat because I have too many.
I will do
so
that.
one question: are there ready packages for color cameras?
No, we don't have a package for cameras yet. We do have one for displays. We also have, if somebody needs to, we have unpublished packages for e-ink displays, but not published them yet. The cameras need I2S, parallel I2S, which we just haven't implemented yet. It's a relatively big thing. We all know the ESP32 cam is great, cheap and everything, but in terms of effort compared to other things that we would like to have, it never made it to the top. Not yet.
So it's on the long roadmap, so to say.
Eventually, obviously, we want to have it. I mean,
Yeah.
I have several ESP32 cams lying around. It would be great if I could just use them.
Yeah. So one question about services. So if you while processing messages from one Toit servers, will other services will they be blocked, or how does that work?
This is where basically multi-threading comes into account. So since each process is actually running in a real process in some sense, I mean, each application is running its own process, they are multi-threaded. If you basically, since we have two cores, it can even be that these two run in parallel. When you ask a service for something, it's basically an RPC request of send me the data back, and how that's implemented, if two ask at the same time, how that blocking works, I actually don't know, but I'm guessing that you could decide of whether, I mean, you have only one application running, so it would need to be serialized. I mean, but I'm not sure if they can handle the requests in parallel like you do in the HTTP server, or if you need to finish one before the other one can work. But that's changeable too.
And now there is yet another question. Well, how does it look with like you mentioned over-the-air updates. So now you're on the same local area network and you're running in a development setting, so to say. So if you have 1,000 devices at, customers' houses or whatever, or an industry. So how does that look? Is this implemented just yet, or?
We have customers that implemented themselves. The Jaguar itself is open source, so and it's only about, I think, 500 lines, of which 200 is just the HTTP to show a nice website when you click on the link that is shown in the beginning. What I'm trying to say is that if you want to, you can implement this already now by yourself, by adapting Jaguar. We are working on this, and a stable version of this is basically where we want to sell. So this is where our company wants to make money on. We had a version 1, so you will sometimes hear V1, V2. We had a version 1 where we did this already, but we are changing a little bit of how this works. So this is work in progress, and within the next 1-2 months, we want to have a prototype of how to do this. And the really stable how to update with with patches that are smaller than, where you have a patch that looks at the previous version and only sends the changes and so on, and make sure that if that fails, it doesn't, it's not bricked and similar things. That's the service we want to sell. But if you look at Jaguar, you will see you can easily do a request to a server, HTTP server, download it and install it, and it will work. So updating works.
Yeah, and when you say version 1, I looked actually, if you go into toit.io, that is what you mean with, but version 1, that's like what?
Yeah, so we in version 1, we had our own server, our own service where you went to, which was console.toit.io. It's still running, and we didn't turn it off. And we were basically handling we proposed the fleet management through our servers. So when you installed something, you went through our server, and our server then pushed it down to the devices that you owned. But we heard that, I mean, and for good reason, that it's not something that people want to depend on. If we go down, then all the devices are suddenly not reachable anymore. It was just not a very popular, not very, we needed to change it. And
Yeah.
with the two, we're going to make this better.
Yeah. So maybe we need to wrap it up, but I like take two last questions. Like the energy consumption for Toit on the ESP32 compared with like MicroPython or any other programming language, let's say C++ or.
Okay. So you will always be better off with C and C++. You just can't beat that. On the other hand, you pay for it. The consumption itself, I would say you pay generally for the time you run. So if Toit is 10 times faster than MicroPython, you should finish your tasks 10 times faster. Yeah. That said, a lot of the time you're waiting. So if you're on Wi-Fi, you're going to wait for the other side to respond and similar things. And also Wi-Fi, Bluetooth, anything that is basically wireless requires the most energy. So fundamentally, it's probably not going, even MicroPython, to be fair, it's probably not going to be the thing that will make the most battery difference. If you can make your requests efficient in terms of time and in how long you deep sleep, you're going to win. That's the most important thing, not waking up.
And I think the last question, and a question I think is already answered, but let's just iterate back to that once again. So is Toit available for other architectures than the ESP32?
It's only available for desktops and ARM machines. I mean, we do have a Raspberry Pi version, and we use it on Linux, Windows, and Mac.
Yeah, and the only microcontroller is the ESP32.
Not yet, no.
Yeah, if I understand the question correctly, the Toit can only be run on the ESP32 microcontroller. Yeah.
At the moment.
Yeah. Okay. In that case, if there are any more questions, I guess that Florian, you could join in for the YouTube chat. And it's not shown here, but I know also that you have a really good Discord server that is quite active.
If you go to toitlang.org, we have a symbol for Discord, and just hop in. We will try to. So this is something I probably shouldn't really say this way, but we do know that our documentation isn't perfect. But on the other hand, we do try to also be very reactive if you have questions. So don't despair if you don't find something, just hop in and ask. It's significantly easier for everybody.
Yeah. So in that case, I'll thank you very much, Florian, for taking the time to be with us in the Connect Them All seminar series. And as Anna said in the beginning, we are now this is the first session, and we will do this monthly from now on. And I want to also give a heads up that the next session will be from Samo Grasic, and that will be about IoT in extreme conditions and delay-tolerant networks. So that for sure will be an interesting session. So please keep yourself updated by checking out connectthemall.net. Follow us on Twitter, and not sure if we are on other places at the moment, but please keep yourself updated. So with those words, thank you very much, Florian.
Thanks for having me.
Goodbye, everyone.